And thanks to Neil and the organizers for the invitation to speak. And I'm so sorry I can't be in London this beautiful time of year. And as you just heard from Neil, the title of my talk is Quantum Field Theory and Invariance of Smooth Four-Dimensional Manifolds. So this is the outline of the talk. I'll say some very general words about physical mathematics, and then we'll zero in on the mathematical and physical problems of interest. I'll talk a little bit about instantons and Donaldson invariants. That will lead me to topological field theory and the physicist's trick known as low energy effective field theory. And then in the last 23.5 minutes, I'll talk about more recent developments, including results on the so-called U-plane integral or Coulomb branch integral, and outline directions for future research. All right, so what is physical mathematics? Well, it's a noun. That's how it's pronounced, both in British and American English. The definition is that physical mathematics is a fusion of mathematical and physical ideas motivated by the dual but equally central goals of elucidating the laws of nature at their most fundamental level, together with discovering deep mathematical truths. So we don't have time to talk about the entire history of mathematics and physics. It's centuries and centuries old, but this combination of finding deeper, sophisticated mathematics as a way to move to more fundamental physics can certainly be traced at least as far back as Dirac's paper on magnetic monopoles, where he introduced fiber bundles into physics and also predicted a new elementary particle. And he begins his paper in this exuberant way. The steady progress of physics requires for its theoretical formulation a mathematics that gets continually more advanced. And it seems likely this process of increasing abstraction will continue in the future, and the advance in physics is to be associated with a continual modification and generalization of the axioms at the base of the mathematics. And around the same period, Einstein in various lectures made similar optimistic and enthusiastic statements. But then towards the middle of the 20th century, physics and mathematics diverged somewhat, so much so that in 1972, in a very famous paper, beautiful paper by Freeman Dyson, he famously proclaimed that as a working physicist, I am acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. Well, I'm happy to announce that mathematics and physics have remarried. The change began around the same time that Dyson was writing those words, when some great mathematicians got interested in aspects of fundamental physics, while some great physicists started producing results requiring ever-increasing mathematical sophistication. So that in the past few decades, a new field has emerged with its own distinctive character, its own aims and values, and its own standards of proof. And one of the guiding principles is certainly the discovery of the ultimate foundations of physics. As predicted by Dirac, this quest has led to ever more sophisticated mathematics. But a second guiding principle is that physical insights can lead to surprising and new results in mathematics. And such insights are a great success and just as profound and notable as an experimental confirmation of a theoretical prediction. So today, I'll explain just one emblematic, paradigmatic example of a remarkable convergence of physical and mathematical ideas. So let's talk about the mathematics and the physics problems that we're going to address. On the math side, we're going to talk about four-dimensional differential topology. So X will stand for four-dimensional, compact-oriented, simply connected, smooth manifold without boundary. Now, as opposed to two dimensions, we do not know anything even close to a complete topological invariant. And one thing we know for sure is that the world of such four-dimensional manifolds is really wild, so that leading experts in the field will write papers like this one with titles that you can read. On the physics side, for the mathematicians in the audience who don't think much about physics, I want to tell you just one elementary thing about the nuclear force. So in grade school, we all learned this picture of the atom. This picture is highly inaccurate in many, many ways. And one of the ways that it's inaccurate is the scale. So if we scaled up the size of the atom to the size of the screen in this auditorium, I'm guessing it's about 3 meters or so, the size of the nucleus would be a little bit larger than that of a bacterium. So it's really cozy in there in the nucleus. The typical nuclear distance scale is 10 to the minus 15 meters. But the protons have positive electric charge, and same sign electric charge repels. And the electrical force goes like 1 over the distance squared. So the electrical force between the protons is producing an acceleration. Well, how big? Just for comparison, on the fastest roller coaster you'll ever take, you will briefly be subjected to an acceleration of 6 g factors. Fighter pilots can briefly withstand accelerations of 9 g factors. The protons are experiencing an acceleration on the order of 10 to the 28th g factors. So why is the nucleus stable? Why is matter stable? Because there's an opposing attractive force, aptly named the strong force. And the strong force is very subtle. It's been studied with particle accelerators for decades up to the present day, including at the Large Hadron Collider at CERN. The mathematical formulation of the strong force involves Yang-Mills theory. So we introduce a compact Lie group G, finite dimensional, and its Lie algebra is small Gothic G, and it's equipped with an invariant bilinear form, which I'll just call trace. And we'll let script A be the space of connections on principal G bundles over X, so that A mod G is the space of connections up to isomorphism, the gauge equivalence classes. So now if we're given a connection on P and a Riemannian metric on X, then we can form the Yang-Mills action. So capital F here is a two form valued in the Lie algebra, and the Hodge star is a map from two forms to two forms, and it depends on the Riemannian metric on X. So this is gauge invariant, and so it descends to a function on A mod G. Now, formally, there exists a natural translation invariant measure on script A, which pushes forward to a measure d mu on A mod G. And the physicists want to believe that d mu times e to the minus Yang-Mills action is a well-defined probability measure on A mod G. And expectation values with respect to that measure are called path integrals. Now, whether this really exists as a mathematically rigorous object is literally $1 million question, but the overwhelming evidence suggests it does make mathematical sense, and I will assume that it does in the rest of this talk. So now we're going to talk about instantons and Donaldson invariants. So as a preliminary, let me remind you about self-duality in 4 dimensions. So the Hodge star is a map from two forms to two forms, and it squares to 1. So for any two form, we can project onto the self-dual and anti-self-dual parts, omega plus and minus. And the space of harmonic two forms then splits into an orthogonal sum of self-dual and anti-self-dual forms of dimensions B2 plus and minus. Now, by Hodge theory, we can identify the harmonic forms with the second cohomology. So B2 plus B2 minus is the dimension of H2 of X. And those are also the dimensions of the maximal dimension subspaces, which are positive or negative definite under the intersection form. So now, what are the most important connections in this probability measure? Well, they will correspond to the minima of A Yang-Mills. Now, the Yang-Mills action is essentially the norm squared of the curvature. So you would expect that you can minimize it by setting the curvature to 0, f equals 0. But in general, we cannot set f equals 0, because if we consider this integral, that's a topological invariant. That's locally constant on the space of all connections A. And the integer k depends on the topology of the principal G bundle. And in fact, we can take our space of connections and it's a disjoint decomposition over connected components labeled by k. So each of these A sub k's is an infinite dimensional affine space. So to minimize in a sector k, we uncomplete the square. So here it is again. And the first term is positive semi-definite. So if we have a solution of the anti-self-dual Yang-Mills equations that sets f plus to 0, we will minimize the action in that sector. Notice that such solutions can only exist when k is greater than or equal to 0. So solutions to f plus equals 0 are called instantons. And ever since their discovery in 1975 by Belavin, Polyakov, Schwartz, and Tyupkin, they've been intensively studied by physicists interested in Yang-Mills theory, and especially in the 1970s and 1980s, the physicists were having a great time playing with this new toy, the instantons. Lots of fun. Well, meanwhile, back at the ranch, the mathematicians, such as Atiyah, Bott, Drinfeld, Hitchen, Manin, Singer, Uhlenbeck, were producing remarkable mathematical results about these instantons. And among other things, they come in continuous families called the moduli space of instantons. So M is a subspace of A mod G. And it too decomposes into connected components labeled by K. Each of these MKs is finite dimensional, and at a generic smooth point, it's a finite dimensional manifold whose dimension was computed by Atiyah, Hitchen, Singer using the index theorem. So the formula for a simple Lie group is 4hk, h is the dual Coxeter number of G, minus the dimension of G times the Euler character chi of the four-manifold, plus the signature sigma of the four-manifold over 2. So for G equals SU2 or SO3, it's this explicit formula. But I do want to stress that the moduli space depends on a choice of Riemannian metric on X. Now, Atiyah and Hitchen had a student, Simon Donaldson, who made a remarkable observation. He said, supposing we have a smooth surface S in our four-manifold, then we can pull back the gauge connection to S and then consider the Dirac equation coupled to that connection. So now we consider those instantons such that if we pull back the connection and look at the Dirac equation, it has a solution on that surface. Call that subspace M of S. The homology class of M of S only depends on the homology class of S in the four-manifold. And the Poincare dual to that homology class is a cohomology class mu of S of degree 2. So Donaldson told us to consider this function of the homology class. Or if you prefer to work in finite dimensions, just expand out the exponential. So mu of S is a linear function of S, and Z Donaldson of S is a function on H2 of X. And Donaldson's discovery is that even though the moduli space depends on the metric, these intersection numbers are metric independent, and therefore are topological invariants, smooth invariants of the four-manifold X. Now, the discovery of these and related topological invariants by Mike Friedman led to major advances in the differential topology of four-manifolds, for which they shared the Fields medal. So Friedman is second from the left, and Donaldson is on the far right. And so all was sweetness and light, except that the Donaldson invariants are extremely hard to compute. It took a lot of effort to compute just a few special examples, and mathematicians seem to have hit a wall. But then came topological field theory. A turning point was when Michael Atiyah asked an important question. Okay, you physicists gave us the instantons, we mathematicians have produced the Donaldson invariance. Well, what's the physical interpretation of the Donaldson invariance? And one physicist that listened was Edward Whitten, and he went and thought about it. And his answer is that the Donaldson invariance can be computed within the framework of a Yang-Mills field theory with gauge group SU2. So here's his paper. And in the course of answering Atiyah's question, he invented the concept of topological quantum field theory, which continues to be an important topic of mathematical research up to the present day. Very active field. Now, more specifically, Whitten told us to look at an n equals 2 supersymmetric Yang-Mills field theory. So what are the fields in that theory? Well, there's the gauge connection because it is a Yang-Mills theory. And then there's a scalar field, which I'll call the Higgs field, which is a section of the complexified adjoint bundle. And then there are fermions, which are anti-commuting fields, which are sections of the adjoint bundle, tensor the chiral spin bundle over X, tensor a rank 2 complex vector bundle, which has its own connection and structure group, which is also SU2, but that should not be the green SU2 should not be confused with the gauge group of the theory. That's a global symmetry of the theory. And indeed, the n equals 2 of super Yang-Mills theory is the same as the rank 2 of this complex vector bundle and the structure group SU2 in green. Now, a lot of the fun in Donaldson theory comes with manifolds which are not spin. If X is not spin, then you can't define the chiral spin bundle, but you can make a choice of E so that the tensor product, S plus tensor E, is well defined, even though the separate factors are not. Oh, in super Yang-Mills theory, we replace the probability measure on A mod G by a supermanifold, script F, which is fibered over A mod G, but there's still a formal probability measure, or more properly, a Berezinian, and it's weighted by e to the minus super Yang-Mills action, which looks like this. So the first term is the Yang-Mills action. Then we have the norm squared of the derivative of phi and square of the commutator of phi and phi adjoint, plus some fermionic terms, plus some interactions. So it turns out that for special choices of E and the connection nabla E, the variation of the measure with respect to the metric on X is a total derivative, so that the path integral is, at least formally, a topological invariant. That observation is called topological twisting. And now in this theory, you can include observables. So if S is a smooth surface, then you can introduce an operator where you integrate phi times F over the surface, and you consider the expectation value of e to the O of S. With the topological twisting, namely the special choice of E and nabla E, O sub S only depends on the homology class of S, so that Z sub W of S is a function on the homology, and it's independent of the metric. That should all sound very familiar, and indeed Whitten proposed that Z Whitten of S is Z Donaldson of S. Now, further insight into why that is so was given by a paper of Atiyah and Jeffries. The measure can be interpreted as a representative of a tome class for the normal bundle of this moduli space inside the space of A mod G. And that implies that the path integral over F localizes to an integral over M, which in any given connected component is a finite dimensional integral. And then furthermore, Beaulieu and Singer argued that under this localization, Whitten's operator O of S pulls back to Donaldson's class mu of S. So this is the reason for the claim that Z Donaldson of S is Z Whitten of S. And all was sweetness and light, except that Whitten told us to compute in a quantum field theory. So computing Donaldson invariance a la Whitten requires computing expectation values in a Yang-Mills theory. How hard can that be? Well, here it's important to make a distinction between Abelian field theory, the paradigmatic Abelian field theory being Maxwell's theory of electricity and magnetism, and non-Abelian field theory, such as the theory that governs the strong force. Now, quantum Maxwell theory and quantum electrodynamics are hard, but solvable for all practical purposes, as was discovered by Dyson, Feynman, Schwinger, and Tominaga in the middle of the 20th century. The non-Abelian case is much to the nth power harder and not solved to that degree that QED is solved. So computing correlation functions of operators in non-Abelian Yang-Mills theory is extremely difficult, and we seem to have exchanged one hard problem for another. But the physicists have a trick called low energy effective field theory. So we observe that this Donaldson-Witten function is independent of the Riemannian metric Q mu nu on X. So now let's consider scaling the metric up, multiplying by L squared and taking L to infinity. In quantum theory, length is inversely proportional to energy, so that's the same thing as looking at ultra-low energies. Now, I won't carefully distinguish between the minima of energy and action. Let's call either one vacua. Small deviations from a vacuum can be described by a different quantum field theory known as the low energy effective theory. So the idea is that we ask a question Q in a quantum field theory with action A, and Q is the question we really want to answer. But we answer the question using a different quantum field theory with action A, low energy effective theory, which perhaps has a totally new set of fields. But the answer to Q is the same as the answer to an analogous question, let's say Q, low energy effective theory. And the idea is that calculations might be easier in the low energy effective theory. So let's see how that works in our case. So it turns out to be very fruitful, first to understand what are the vacua on R4. So here again is the super Yang-Mills action, just the part for the bosonic field. It's a sum of squares, so we can minimize it by setting each of the three terms to 0. We're on R4, which is the bundle will be topologically trivial, so there's no obstruction to putting F equals 0. And if F equals 0, the gauge connection is equivalent to the trivial connection. So setting d phi equals 0, the vacuum has phi of x constant, so it's just some vector in the Lie algebra of the gauge group. And then it has to be a vector such that phi computed with phi adjoint is 0. Particularly, that implies that phi is diagonalizable. But any constant phi will do. So there's not a unique vacuum. There's not a unique Poincare invariant vacuum. There's a moduli space of vacua. And thanks to non-renormalization theorems, this persists in the quantum theory. So the upshot is that there exists a family of Poincare invariant quantum vacua parametrized by some continuous parameters U. For the case of the gauge group SU2, U is just in the complex plane, and we can characterize it by saying that in the vacuum omega of U, the expectation value of trace phi squared is the complex number U. So there's not one probability measure, but for SU2, a continuous family labeled by U in the complex plane. Now, at a generic point on the complex plane, that vacuum exhibits spontaneous symmetry breaking. So thinking classically, at a generic point U, the vacuum is gauge equivalent to a diagonal matrix with a generic value of A. And the gauge transformations that map phi vacuum to itself, they act in the adjoint representation, so they just conjugate by a unitary matrix, and the only unitary matrices which conjugate this to itself are diagonal. So the automorphisms of the vacuum are just U1 gauge transformations, which translates into the statement that the low energy effective theory of small field deviations around a vacuum U is an Abelian gauge theory. Now, what is that Abelian gauge theory? Well, that's the question that Seiberg and Whitten answered in their breakthrough paper in 1994. So the low energy effective action has effective theory has an action that depends on U, and Seiberg and Witten's discovery is that it can be computed from the periods of a meromorphic one form called the Seiberg-Witten differential on a family of Riemann surfaces called the Seiberg-Witten curve. And for G equals SU2, here's the explicit formula. It's a family of elliptic curves parameterized by U with an explicit meromorphic one form on that elliptic curve. That elliptic curve also parameterizes other physical aspects of the theory. Because it's an Abelian gauge theory, there are electric and magnetic charges. And the electric and magnetic charges, as Dirac taught us, live in a symplectic lattice. The electromagnetic charge lattice can be identified with the first homology lattice of the Seiberg-Witten curve. Now, a subtle point is that the low energy effective theory only depends on this pair of the curve and the meromorphic one form. But in order to write an action, we must choose a splitting of the electromagnetic charge lattice into maximal Lagrangian sublattices. In our case with SU2, we have to choose an electric charge and a magnetic charge. Mathematically, that's choosing a basis of the elliptic curve, so that data gives us a period matrix tau of U. Once we've done that, we can write the low energy effective action. It looks like this. F here is the Abelian field strength with its self-dual and anti-self-dual projections. And tau of U is the coupling constant. Now, different low energy effective theories with different splittings are still the same theory, but they're related by a transformation of fields known as electromagnetic duality. Now, another interesting wrinkle is that this family of symplectic lattices has non-trivial monodromy around the discriminant locus, where the discriminant of the elliptic curve vanishes. So the picture you should have is that over a generic point in the U-plane, you have a nice smooth elliptic curve. But at two special points, that's the discriminant locus, one of the cycles of the torus pinches and the curve degenerates. Because of that monodromy, we cannot use the same gauge field for all values of U. The transitions from one patch to another are given by electromagnetic duality, and in particular, the low energy effective theory breaks down near the discriminant locus. But in the neighborhood of the discriminant locus, we can use a different low energy effective theory where there are new fields known as monopole fields, which need to be included. It's also an Abelian gauge theory, and it has its own action. I'll call it A upper UJ. Now let's return to the four-manifold X, which is compact. Because of quantum effects, when we do the path integral for a compact X, we have to sum over all the vacua on R4. And there are two kinds of vacua. There's the continuous moduli space of vacua parameterized by U that we've been discussing. But also near the discriminant loci, there are these new low energy effective theories, A upper UJ. And each of these has its own set of vacua, and those are enumerated by solutions of the renowned Seiberg-Witten equations, which I'll write down later. So when we want to evaluate this Donaldson-Witten function using the low energy effective theory, well, here's Donaldson's definition, here's Witten's definition. We've argued they're the same. Using the low energy effective theory, we have an integral over the U-plane and a sum over the points in the discriminant locis. For SU2, it's just 2 points. So let me make some preliminary comments about ZU. It's an explicit integral over the complex U-plane computed using quantum field theory techniques. We will return to it and discuss it in some more detail later. But first, let's finish writing down the full answer for the path integral. What about those contributions from the discriminant locus? Well, the path integral for that low-energy effective theory takes the general form of a sum over vacua, namely solutions to the Seiberg-Witten equations. Those are enumerated by spin C structures, which for our purposes are just integral lifts of the second Stiefel-Whitney class of the tangent bundle of X. So the contributions from the discriminant locus look like a sum over spin C structures of this renowned Seiberg-Witten invariant, which is a sum, a signed sum over the different solutions of the Seiberg-Witten equation for a fixed spin C structure, times a function of S, which is a complicated formula here. It's a residue of a certain differential form on the complex U plane. The stuff in green can be computed from the Seiberg-Witten curve directly. This omega of u is a non-vanishing period in the neighborhood of uj, and t of u is given by a certain Eisenstein series. But then there are holomorphic functions, c, p, and e, which are raised to a power given by a topological invariant, like the Euler character and signature. But these are not known a priori. You can't look up C, P, and E in the Seiberg-Witten paper. They're independent of the four-manifold, but they're difficult to compute from first principles. Nevertheless, using a phenomenon known as wall crossing, you can actually derive C, P, and E directly from the U-plane integral. And that's why the U-plane integral is of fundamental importance. It allows you to get the whole answer. In particular, you can derive the Whitten conjecture. When B2 plus of the four-manifold is bigger than 1, because of fermion zero mode, ZU is 0. So if X has B2 plus bigger than 1, then the only contribution is from the discriminant locus. There are 2 points in the discriminant loci. So here we have a sum of 2 terms. We sum over the spin C structures weighted by the Seiberg-Witten invariance, and that residue, that complicated residue, boils down to some very simple trigonometric function of the various topological invariants. So for example, for K3 surfaces, the Donaldson-Witten function of S is just the hyperbolic sign of the self-intersection of S with itself over 2. So the Donaldson invariants can be written in terms of the Seiberg-Witten invariance. They carry the same information about four-dimensional space, but they're much easier to compute, those Seiberg-Witten invariants. So it's like trying to do a calculation with a slide rule or with Mathematica on your laptop computer. It's clear what you should do. Now here I want to make a sociological comment. You know, when a physicist gets a good idea, then she or he will think about it over the weekend and get the paper out the next week. And then all the low-hanging fruit, all the easy computations with very important consequences are on sale. And the physicists all rush in and write papers, and there's a great frenzy. On the other hand, when a mathematician gets a good idea, then she or he will think about it over the weekend, and then over the next week, and then over the next month, and maybe the next year or 2. So that when the paper comes out, it's like a beautiful Greek temple with all the logic perfect and all the consequences perfectly worked out. Except in this case, the mathematicians behaved like the physicists. So when Whitten wrote his paper on monopoles and four-manifolds introducing the Seiberg-Witten invariance, there was this mad rush by the mathematicians. It was a major breakthrough in four-manifold theory, a real paradigm shift. So now I'd like to make some other comments on the Whitten conjecture. It agrees with a structure theorem of Kronheimer and Mravka, whose work indeed provided important background for Whitten's conjecture. The physical derivation I just sketched was in a paper of mine with Whitten in 1997. There's a rigorous mathematical proof for complex surfaces by Gutcha, Nakajima, Yoshioka. And Paul Fian and Tom Liness have worked for a long time outlining a rigorous proof of this conjecture using standard techniques of differential geometry. So now I'm going to take the last 26 minutes. I think I went a little too fast, but I'm going to take the last 26 minutes to talk to you about more recent developments. I mean, this is a beautiful story, but it's an old story. So why am I talking about it today? Because in the last few years, there have been some nice developments, understanding deeply aspects of the U-plane integral, and also starting to move along lines of new developments, new directions in this general area. So first, I want to tell you about some new results on the Coulomb branch integral, the U-plane integral. So as I said before, it can be computed explicitly from quantum field theory of the low energy effective theory. It vanishes if B2 plus is bigger than 1. When B2 plus is equal to 1, it has this form. It's an integral over the complex plane for SU2, where of a product of a holomorphic and metric independent function that turns out to be related to modular forms, and psi, which is a sum over the principal U1 bundles for the Abelian gauge field of the low energy effective theory. These are principal U1 bundles over the four-manifold X. So very roughly speaking, psi has this form. So for each first Chern class, we take a harmonic representative and consider its self-dual and anti-self-dual projections. And we weight that by the coupling constant, which is the period matrix of Seiberg and Witten's curve. Now notice that this psi function is not holomorphic, and worse, it's metric dependent because it depends on self-dual and anti-self-dual projections. So it looks bad for a topological field theory, but one can hope that nevertheless the integral over the U-plane will be independent of metric. And that turns out to be indeed almost true. It's piecewise constant as a function of metric, but it will jump across real codimension 1 walls. Now, this U-plane integral turns out to be closely related to the theory of Mach modular and Mach Jacobi forms. Special examples of this phenomenon were noted a long time ago, but the new point is that the relation holds for all four manifolds with B2 plus equals 1. And I think that was explained most conclusively in a paper I wrote with Jan Manscott from Dublin and graduate students George Korpas and Yuri Nadayev back in 2019. So I want to tell you a little bit about what we said. So here's the Seiberg-Witten family of elliptic curves. And now as we go around the circle at infinity, then we find a unique cycle, which is invariant under monodromy. Let's call that the A cycle. So that gives us one period. And then we just have to choose another cycle, a complementary cycle, the B cycle. And then you can compute with hypergeometric functions or something like that. You can compute the ratio of these integrals. But importantly, you can invert your function tau as a function of u to give u as a function of tau. So the thetas here are Jacobi theta functions. So you can write u as an explicit Q series, where Q is e to the 2 pi I tau. And this u is a modular function for the congruent subgroup gamma upper naught 4 inside SL2Z, which has the fundamental domain that you see in front of you. And you could take the various pieces of that domain and you can map them all into the so-called keyhole region, which is a fundamental domain for SL2Z. So the keyhole region is the region bounded by the blue lines. So at the end of the day, this U-plane integral ends up being a sum of integrals of this form. An integral over the keyhole region of m tau to some power times a function f, which is a power series in q and q bar, with the powers of q and q bar bounded below. So the strategy for doing this integral is to try and do it by parts. So you try and find a function h hat such that d by d tau bar of h hat is the integrand. And then you have to integrate h hat around the blue boundary. Now, in general, that will get you nowhere. It'll just give you some complicated integral around the blue boundary. But if h hat is modular of weight 2, 0, then the contributions from the blue boundary cancel, and all you're left with is the boundary up at infinity. So now the general solution of the differential equation looks like this. It's a holomorphic function h of tau plus r, where r is some explicit solution of this simple first-order differential equation. It's not hard to solve this differential equation. It's a first-order differential equation. So you choose a solution which vanishes exponentially fast as m tau goes to infinity. That's not hard, but then that r is not modular. If there exists a holomorphic function h of tau such that the sum of h and r is modular, then we say that h of tau is a Mach modular form. H of tau will have its Q series, and if you try and take its modular transformation, it starts out nicely, but then it has a correction point. It's not quite modular. But h hat of tau is modular. So if you can find this h hat of tau, then it's a piece of cake to do the integral. Because as I said, the blue boundaries cancel, and all you're left with is the integral across the strip out at m tau goes to infinity, and that picks out the constant term in the Fourier expansion of h of tau. So notice that that constant term is undetermined by the differential equation. It's fixed by the modular property, so it's rather subtle. Now, there's a long history of the definition and evaluation of integrals with singular modular forms like this. And here I've listed some of the main references. And the red references are primarily math papers. The blue references are primarily physics papers. And so you see this alternating red and blue. It's a nice math-physics dialogue, which is just a sub-story of this bigger story of four-manifold invariance. Okay, so in the last 20 minutes or so, I want to tell you about directions for future research and some of the more recent work that's been done in this area. What about the future? Well, there are many future directions. We could talk about other n equals 2 theories. We could talk about family invariance. We could generalize to four manifolds with B2 plus equals 0. Then there's the generalization to manifolds with boundary and floor theory. There's a generalization of Seiberg-Witten invariance called the Bauer-Furuta invariant, which is begging for a physical interpretation. And then there are so-called K-Theoretic and elliptic generalizations. So I'm only going to have time to talk about other n equals 2 theories, family invariance, and K-Theoretic and elliptic generalizations. So first about other n equals 2 theories. So Whitten's formulation of Donaldson theory made use of a very special, particular n equals 2 quantum field theory. That's called super Yang-Mills with pure super Yang-Mills with gauge group SU2 with only the minimal set of fields. But there are infinitely many other four-dimensional n equals 2 supersymmetric quantum field theories. At least in principle, the topological twisting should make sense for any n equals 2 theory, because the key feature of topological twisting makes use of that global symmetry group, which I called SU2R. Although, if you look carefully at the details, there are t-dependent details which actually remain to be worked out. So I think many people are taking it a little bit too much for granted that you can topologically twist. But I have no doubt that it can be done. So the natural question is, given the more than successful, the spectacularly successful application of n equals 2 super Yang-Mills for G equals SU2 to the theory of four-manifold invariance, are there other interesting applications of other n equals 2 field theories? Now, one important class of n equals 2 field theories are the Lagrangian theories. So we should say, how are these Lagrangian theories generalizing Donaldson invariance? So you can imitate all the things that Whitten said. And then the localization takes you to an integral of some characteristic classes over, importantly, a moduli space M, which is not the moduli space of instantons. It's the moduli space of solutions to this set of differential equations. So here, M, the so-called monopole field, or non-Abelian monopole field, is a section of a chiral spin bundle associated to a spin C structure, W plus, tensor with a vector bundle V depends on what particular theory we're looking at. So you first solve the Dirac equation for this m, and then use m and its complex conjugate, combining them in a quadratic expression to get a self-dual 2 form, and you set that equal to f plus. So these are called the generalized monopole equations, or the non-Abelian monopole equations, and they were written by various people shortly after Whitten introduced the U1 case, the Seiberg-Witten equations, that set off that revolution in four-manifold theory. Now, one example of this, alternate theories to look at is the case of what the so-called n equals 2 star theory. So here the monopole field is valued in the chiral spin bundle tensored with the complexified adjoint bundle. And I studied that in great detail recently with Jan Manscott. And let me just tell you a little bit about what we found. So first of all, this theory depends on a choice of spin C structure. Indeed, you see that. That's what I meant by W plus. It's the chiral spin bundle for that spin C structure. And it depends on it through the characteristic class of the spin C structure. And then this theory has a property called superconformal invariance. So it depends on a point in the upper half plane. And that is not to be confused with the Seiberg-Witten tau of U. This is a point in the upper half plane that has to be specified just in order to define the theory in the first place. And the statement of S-duality is the statement that, in fact, the theory doesn't depend just on the point on the upper half plane. It only depends on the elliptic curves determined by that point. And finally, there's a deformation parameter, which I'll just call T, which for physicists is the mass parameter divided by a dynamical scale, MD. So the analog of the Donaldson-Witten function is a function on the homology that now depends parametrically on the point in the upper half plane, a spin C structure, and a deformation parameter T. And it's given by this expression where we sum over integrals over the non-Abelian monopole solutions. We weight this with an Euler class, which is an equivariant Euler class for the U1 symmetry that rotates the monopole field. And the curly E here is an obstruction bundle for an elliptic complex associated with the non-Abelian monopole equations. So this is a very interesting function. It interpolates between the Donaldson-Witten invariance as t goes to infinity and the Vafa-Witten invariance for t goes to 0. It's suitably S-duality covariant under SL2Z transformations of tau uv, but it's not holomorphic in tau uv for B2 plus equals 1. It is holomorphic when B2 plus is bigger than 1. And there's been a lot of confusion about that over the past few decades, but I think my paper with Jan really settles that pretty nicely. And there was parallel work done for the n equals 4 Yang-Mills theory done by Atish Dabelkar, Pavel Putrov, and Edward Whitten. We were studying different theories, but it settles the issue of the holomorphic anomaly pretty nicely. There are exact expressions in terms of Jacobi mass forms as a function of tau uv. And there's an explicit analog of the Whitten conjecture for B2 plus bigger than 1. Now, what about other n equals 2 theories? So there's a set of theories called class S. So this will be the first of 3 conjectures I'll use to end the lecture. So there's another class of 4-dimensional n equals 2 theories, which are derived from 6-dimensional quantum field theories by compactification on a Riemann surface C. And these are not always described by an action principle, so they're a little bit more mysterious. So my first conjecture is that for all Lagrangian and all class S theories, the four-manifold invariance will ultimately be written in terms of the Seiberg-Witten invariance using formulae that generalize the Whitten conjecture. So there's some non-trivial checks of that. So for pure SUN theory, that's a Lagrangian theory. Marcos Marino and I checked that about 20 years ago, more. And a few years ago, for the simplest of these class S non-Lagrangian theories, I checked this with my student, Yuri Nadayev. But the general case is very much a conjecture. And even if you can express them in terms of Seiberg-Witten invariance, that doesn't mean they're uninteresting. For example, Mourinho Perazza and I discovered new interesting properties of Seiberg-Witten invariance by studying other theories. So you can still find interesting new facts by studying these other theories. Okay, now I want to talk about the second direction, the family Donaldson invariance. So there's an interesting generalization to invariance of families of four manifolds. This, in fact, was mentioned by Donaldson long ago, and a modest amount of work has been done in the math literature, but basically nothing in the physics literature. So Donaldson's idea is that now the Donaldson function is going to be valued in the cohomology of the classifying space of the diffeomorphism group, the oriented diffeomorphism group of the four manifold. So in a project with Jay Cushing, a graduate student at Rutgers, and Martin Roczek at Stony Brook, and Martin's student, Vivek Saxena, who's now a postdoc at Rutgers, we've been studying this from the physics point of view. So to tell you what we did, let me remind you of what we said a little bit a while ago about what Beaulieu and Singer interpreted about Donaldson-Witten theory. So if P is a principal gauge bundle over the four-manifold X, we introduce the infinite-dimensional group of gauge transformations, calligraphic G, the automorphisms of the principal bundle. And Beaulieu and Singer said, what we're really doing is we're studying the G equivariant cohomology of the space of connections on that principal bundle. So in the Cartan model, the complex is written this way. In physics notation, we introduce the Cartan differential Q to take a gauge connection A mu to psi mu, where psi mu has the interpretation of a cotangent vector on the space of connections. And then phi is a generator, degree 2 generator of the symmetric algebra of actually the dual of the Lie algebra of the group of gauge transformations. And that phi is the same as the Higgs field phi I talked about before. And so if we combine Atiyah and Jeffrey and Beaulieu and Singer, what they're saying is this Donaldson-Witten function is a push forward in the G equivariant cohomology. So now let's introduce the oriented diffeomorphism group of the four manifold, call it G sub D. And now we want to study the GD equivariant cohomology of the space of metrics of the four manifold. So in physics notation, we have a multiplet of fields, G mu nu. Psi mu nu is an anti-commuting, an odd field, which is a symmetric tensor on the four manifold. And capital phi upper mu is a degree 2 vector field. So it's an element of the Lie algebra of the diffeomorphisms of X. So the idea is that the action, e to the minus s, will be a closed equivariant class in the G semi-direct GD equivariant cohomology of metrics times connections. And then the push forward along A in G equivariant cohomology will be a GD equivariant class in the space of metrics. So thanks to heroic computations by Jay Cushing and Vivek Saxena, we now have explicit actions obtained by coupling to truncated and twisted n equals 2 supergravity. So the idea is that these G, psi, and phi are the remains of a big truncation and twisting of n equals 2 conformal supergravity, and they are consistent truncations. And then we can couple that to the vector field and get a suitable action. So the claim is, at least formally, that the path integral as a function of these background fields has a cohomology class, which will be a cohomology class on the classifying space of the oriented diffeomorphisms of the four manifold. And so conjecture B is that these will produce the invariants envisioned by Donaldson and generalizations thereof. So in the last 6 minutes, I'll talk about the third of these new directions. So this has to do with so-called K-Theoretic Donaldson invariance. And this is a project that I'm doing with Jan Manscott at Dublin and Shenyu Zhang, who's a postdoc at DAISY Hyun Kim is a professor at Rutgers, and her student Runkai Tao. So, when somebody says to me, K-Theoretic Donaldson invariance, what I would think is that you should take Donaldson's papers, open them up, and everywhere you see singular homology and singular cohomology, you replace it by some other generalized cohomology theory. In particular, in this case, you would want to replace singular homology and cohomology by K-theory. That's not the way the physicists think about it. The physicists think about it in terms of going to 5-dimensional super Yang-Mills theory on a 4-manifold times a circle. You can't topologically twist the whole 5-dimensional super Yang-Mills, but you can partially topologically twist along the 4-manifold directions. And that, as I explained before, makes it independent of the scale of the 4-manifold. So you can imagine shrinking the 4-manifold and getting an effective theory on the circle, S1. And that means we can reduce this to an effective theory of a super quantum mechanics on the moduli space of instantons. Now, for anomalies to cancel, that moduli space had better be spin C. And at the moment we're a little confused about exactly which 4-manifolds lead to a moduli space, which is spin C. But one thing is clear is that there are lots of examples. For example, if X is complex, then M inherits a complex structure, and a complex structure induces a canonical spin C structure. Now, the theory is not topological in the S1 direction, so it's going to depend on the radius of the circle. So now we introduce the dimensionless version of the radius, and then we expect that the partition function is going to be a sum of positive powers of R, which are governed by the dimensions of instanton moduli space, weighted by the integrals over instanton moduli space of the A hat genus. And this is an observation that goes back to work of Nekrasov in the mid-90s. Now, there's an interesting story here involving observable. The 5-dimensional theory has a global U1 symmetry with a conserved 4-form current, which is just the Chern-Weil representative of the Podragin class of the gauge bundle. So we can introduce that as that's a global symmetry. We can introduce a U1 bundle for that global symmetry and a gauge connection on it, and we can let little n be the Chern class of that bundle. And for every n, we can introduce an observable, which is the integral over the Poincare dual sigma of n times S1 of the Chern-Simons of the non-Abelian gauge connection. Or if you prefer, you can write it as a term in the 5-dimensional action that way. So now we can enhance our partition function to be a function of R and N this way. And what that corresponds to in terms of instanton moduli spaces, we're just inserting E to the first Chern class of a certain line bundle over instanton moduli space that depends on N. So what we've done is using both the U-plane integral and independently localization techniques, we reproduce and generalize results from two beautiful mathematical papers. The first by Gocha, Nakajima, and Yoshioka from 2006, and then a more recent one by Gocha, Kuhl, and Williams from 2019. And we expect that we're going to be able to generalize results in these papers. Now, to close, this should also generalize, it's clear from the physics, that this should also generalize to 6-dimensional super Yang-Mills on a 4-manifold times an elliptic curve. So we expect that the A hat genus will be replaced by the elliptic genus of the instanton moduli space. And so my final conjecture is that integrals in elliptic cohomology, by which I mean push forward in the generalized cohomology theory of elliptic cohomology, integrals in elliptic cohomology of distinguished classes in elliptic cohomology, defined by the supersymmetric sigma model with target space the moduli space of instantons, should define smooth 4-manifold invariants. So these would be the elliptic generalizations of Donaldson invariants. Again, we know virtually nothing about these invariants and whether they generalize Donaldson invariance and Seiberg-Witten invariance in an interesting way remains to be seen. So That's not all, folks, not by any means, but that's all I have time for right now. So thanks for your attention.
Thank you, Greg. Thanks very much. This time for some questions. Does anyone have a question? Can you try speaking? I think we can't hear you.
Neil, you should probably repeat the question. First for the audience and also for me.
Okay, I'll try to repeat.
Right.
I can't. That's going to be pointless to try to repeat.
Hi, does this help?
I can hear you, yeah.
Thanks for your talk. That was very interesting. I wanted to ask about a off comment you just made. You said that you felt that for you, what K-theory, K-theoretic generalization should be is you take, say, a Donaldson paper and replace all the singular cohomology with some version of K-theory. Has that actually been done? How much?
That's a nice question. Not to my knowledge.
Cool.
The closest anybody came is the introductory section of the paper of Gupta, Nakajima, and Yoshioka. Their paper, by the way, is limited to projective surfaces, whereas this should really exist for a more general class of four manifolds.
Are there other questions?
I think that would be a good thing to do, unless I'm unaware of some math literature. Certainly the introduction of their paper says some relevant things about that, but I don't think it's been done systematically along the lines I just indicated.
The follow-up, he agrees because he's interested in the connection with modular forms. Ingo.
Hi, Greg. Thank you for your nice talk.
Is that Ingo? Hello,
yeah.
Ingo.
Hi. I have a sort of more basic question. So which of these invariants, or is it known which actually see the smooth structure? Do they all see the smooth structure? Is that clear? Or do some of them only depend on the topology of the four-manifold?
Well, the U-plane only depends on the classical invariance. So it only involves the intersection form on the cohomology and the Euler character in the signature. However, the Seiberg-Witten invariants can distinguish between different differential structures, and that's part of the fun, and that's part of the fun that people had. But there are manifolds which are believed to be homeomorphic but not diffeomorphic, which nevertheless cannot be distinguished by Seiberg-Witten invariants. So it's clear that we haven't gotten to the bottom of this. That's one of the reasons that motivates me to keep looking in the physics for new invariants.
So there would be some hope that the K-theoretic or the elliptic ones could maybe distinguish these?
That's a possibility. That's a possibility. That very much remains to be seen. Now, I didn't have much time for explaining what the results of these two papers look like that we've reproduced. And so far, the results that we have reproduced definitely only involve classical invariants and the Seiberg-Witten invariants. Perhaps something more subtle in the K-theory. I'm more hopeful that the elliptic generalizations will lead to something really new. But we really don't know. Same story for the family invariants.
Are there any other questions? I had perhaps a quick one. You mentioned some of your work was to couple things to conformal supergravity.
Yeah.
Do you think that there's some relation to black hole counting could come out of these?
Interesting thought. I have not I have not thought about that at all. We've had our hands quite full just these actions. Well, Neil, you can really appreciate this.
Yeah.
Conformal supergravity is an extremely complicated thing. And so we've had our hands quite full just getting this truncation and in fact, we obtained the action coupling the topologically twisted vector multiplet to this topologically twisted and truncated conformal supergravity in two ways. One is by working from the bottom up, so to speak, by adding the psi mu is the twisted gravitino. And so we added, it's obvious what to do at first order in the twisted gravitino. You take psi mu times lambda mu nu, where Q on lambda mu nu is the stress energy tensor. That part is obvious. But then adding the higher order terms is not completely trivial. And we did that by successively adding higher and higher order terms in the gravitational fields, psi and phi, which have degree 1 and 2 in the equivariant cohomology for diffeomorphisms. But then Martin and Vivek, being experts on conformal supergravity, rederived exactly the same action by taking the vector multiplet coupled to conformal supergravity and truncating and twisting. And it's highly non-trivial that the two procedures actually lead to the same thing. But as far as applications and doing the path integral, it's all very new. Our draft is being written, and now that we have the actions, finally we can start to think about consequences. But so far, it's been a struggle just to get to the actions.
Okay. Well, let's thank Greg for a wonderful and deep talk.
Thanks for the invitation.
Okay, and I think David Burns wants to give us all some instructions.
Okay, so I should sign off, right?
Yeah. Thank you very much. You feel free to sign. Bye-bye.
Yeah, okay, just a few remarks to ease the transition from Monday to Tuesday. So after this, the